Woohoo! We are live, and today we are going to be helping Godzilla calculate deposits for a sinking fund. Yay! And so the first thing we should talk about is what the heck is a sinking fund? Well, a sinking fund is a business term that basically means saving up for something. So in the problem we're going to be talking about today, a sinking fund is established right there to discharge a debt of $30,000 in 20 years. So in other words, something interesting is happening, and then in 20 years, we're going to have to, or Godzilla is going to have to pay off a $30,000 debt. And so rather than just waiting till then and hoping to win the lottery, Godzilla is going to be saving up to prepare for this debt. You can establish a sinking fund like a savings account. You can be planning to make a big purchase, or like this says, get rid of a debt. So let's talk about what kind of formula we're going to want to use. And so in order to do this, we should talk about it. And the problem says we're going to be making deposits at the end of each 6-month period, and interest is paid at the rate of 2% compounded semi-annually. What is the amount of each deposit? And again, the assumption for this particular class is that all of the deposits will be identical. So it'll be a regular series of payments. So let's think about what's going to be happening. So we have to compare what's happening now with what's happening in the future. The first question is, when do we want the $30,000? Do we need the $30,000 now? So let's take a look at it. And it says we're going to discharge, which means to get rid of or to pay off a debt of $30,000 in 20 years. So the $30,000 we're going to need in the future. So what are we going to do now? Now we're going to make multiple deposits. So if we're making multiple deposits and they're happening regularly, so it says each 6 months we're going to make a payment and we're going to make the same payment. This is an annuity. And this means we're looking for future value. So we want the future value of an annuity. Yay! Woohoo! So thanks to the magic of television, I have this lovely little card put together with the future value of an annuity. Surprisingly enough, almost in identical handwriting. What are the chances of that? And this is the formula. And you'll notice that with annuities, we have a couple of different formulas. I've got S, and I'll review it again on the paper, but S is going to be our future value in both cases. R is our repeated payment, or in this case, the deposit. I've got some I's, that's our interest rate per period. I've got N, total number of periods. And everything here is identical except for this really interesting little guy right here, which I kind of want to highlight in yellow with my handy dandy highlighter, just so that we are multiplying that. So what the heck is going on? Well, let me remind you that when we're talking about an annuity, either an annuity that you're paying into or an annuity that you're withdrawing, regardless of which way the money's going, it matters whether you do it at the beginning of a period or at the end. In this case, if we're making deposits at the end of the 6 months, we've got a regular, ordinary annuity. If we were, say, on the next page, I don't know, if I were going to ask you what happens if we're making the payments at the beginning of each period, well, then that means they're earning a little bit of extra interest. And that's where this 1 plus I comes in. So that's the little bit of extra interest if you deposit the money ahead of time. You get an extra period's worth. Okay, so I'm going to put this to the side as well as we set up our variables. So again, for our future value of an annuity, and this is an ordinary annuity, I'm going to use S equals R times the quantity 1 plus I to the nth minus 1 all over I. And because this is an annuity, I'm sorry, this is an ordinary annuity. Here's my orange. It's at the end. So we use an ordinary annuity because it's at the end of the period. That's it. It's just we're missing out on a little bit of extra interest, but sometimes that can't be helped. Sometimes, for example, perhaps in this business, you're not actually getting money coming in until the end of the month. So you don't have it to make the deposit, or there's something else that's going into the planning. One thing to consider, and I know this is complicated because you don't see, so I'll just have Godzilla kind of come over here and talk to you directly. One thing that you could consider, Godzilla, is that if you know you're going to be depositing this money and this interest is being paid at a rate of 2% and you can earn more than 2%, what you might want to be doing is making sure that your money is currently in another account making more than that. And then just at the last minute each period, you pull it out to make the deposit. Does that make sense? You can maximize your interest? Great. Okay. So we've got our formula. We need to fill in. I'm going to move this over. We got to fill in our variables. Woohoo! So S, which is our future value, is nice and easy because this is what we want in the future. And this would be 30,000. Yay! And then R, our repeated payment, in this case, the deposit. That's what we don't know, right? This says what is the amount of each deposit. So that is the amount we don't know. I need to find I, which is going to be my interest rate over the number of periods per year. So my interest rate is 2%. And it's 6 months. So if it's every 6 months, if it's semi-annual, I have another I have lost all of my colors. I've put my colors somewhere and now they are lost. I think Godzilla ate them. Okay, did you eat them? Were you just really, really, really hungry? So here's semi-annually. So that's going to give us right there 2 periods per year because it's every 6 months. And so that's going to be, I have to write 2% as a decimal over 2. So that's 0.01. Okay, so my interest rate per period is 1% or 0.01. Okay, so far so good. And the last thing we need to know is we need to know how long are you going to do this? Are you going to do this for 2 years or 1,000,000 years? How long is this going to go on? And remember that N is M times T. So that is twice a year times the number of years, which is 20 years. Let's see, I've used purple. I've used orange. I can still use yellow. Here's my yellow right there. 20 years means that I'm going to be making 40 deposits. 2 deposits a year for 20 years. Okay, and then M again is purple. And we are all set up. Now, there's one more thing we might want to do. And that is that this formula, excuse me, Godzilla, this formula is set up to plug in the the repeated payment, or in this case, the deposit, and get out the future value. It is not designed to solve for R. So you've got a couple of options. But since for our class, we have actually studied how to manipulate a formula, I'm going to go ahead and demonstrate how to do this. So let me write this all out. S equals R times the quantity 1 plus I to the n minus 1 all over I. And let me take a moment here and let us solve for R. Honestly, after you've done this a few times, you could probably do this just in your head, because you see you've got the S and the R on opposite sides of the equation, and then you've got this big old numerator and this big old denominator, and basically to move this over, it's just going to flip upside down. What the heck do I mean? Well, if I have S equals the R times this big old numerator all over I, the first thing I could do is I could clear fractions. So I could multiply by I on the left, and I could multiply by I on the right. I did it on the right because I didn't leave enough room here. And then these two i's cancel. So basically I'm clearing fractions. So then I get I times S equals R times the big old numerator. Okay, so far so good. And then what I'm going to do is I'm going to divide both sides by the big old numerator. And then I'm going to cancel this and cancel this. And I end up with R on the right side now. And I'm going to change the order of these two because it looks a little funny to me. I'm going to write S times I all over 1 plus I to the n minus 1. Okay, so let's take a look at the whole thing and see what happened. When the fraction is over here on the right, or the rational expression, I've got the big piece on top and the I in the denominator. I did a bunch of mathematics by multiplying and dividing on both sides, and I end up with the big old fraction or rational expression is on the left. Notice the I, which had been on the bottom on the right, is now on the top. And this big old numerator was on the top. It's now on the bottom. They just flip upside down to get to the other side. So this is now a formula we could go ahead and use. And if you wanted to, this could be one of the formulas that you keep handy and you memorize for when you need to do work like this. Because this is the same formula, but this you get to plug in the future value, the interest rate per period, and the number of periods, and you get out the deposit, if that makes sense. So I'm going to come back. This will be in the notes for this. What I'm going to do is I'm going to go ahead and just write this formula there. I'm going to say R equals S times I. Now, you don't have to put the multiplication in the middle, but sometimes when the S and the I get too close together, it looks funny to me. So I'm writing in the multiplication explicitly. Minus 1. Oh no, I took you to Smearytown, sorry. So, and then I will say, see next page. So this will be in the notes, how I got to this. So this is a slightly different version of the formula. And so, move this out of the way. Thank you so much for doing a wonderful job to help us out. But let's go ahead and plug in the values. So we need the S, that's the $30,000. Remember, we don't put units in when we're doing the math. We're going to multiply by the interest rate, 0.01. Take the whole thing over 1 plus 0.01 to the n is 40, minus 1. So I can simplify things a little bit, or you can do the whole thing in your calculator. For example, I know that this times 0.01 is going to give us an answer. So you can go ahead and simplify it. I'm going to write this just, I'm not going to simplify very much, but I'm just going to remind you that you can write this inside here as 1.01, all raised to the 40th power, and subtract 1. And let's see if we can get a number. Okay, handy dandy calculator. Oop. Oh no, Carol Ann, stay out of the light. There we go. Poor old Carol Ann. Here's Godzilla. Okay, there we go. So we want to make sure our client is watching so they can be very impressed with how smart we are. You want to impress your clients with how smart you are. That's very important. Much better than the opposite. Okay, so I'm going to take 30,000. 1, 2, 3. I'm going to multiply times 0.01, and I'm going to hit equals. You can't quite see it. So that I get the numerator is 300. Now I'm going to go ahead into the denominator. So I'm going to do divided by. Now, because this is two terms, because it's got the subtraction in it, I'm going to start with an open parenthesis. And then I'm going to do 1.01 raised to the 40th power. And then on my calculator, I can go right into minus 1. Now, on some calculators, when you raise something into the exponent, you have to actually pull it back down. So this is an older calculator. It's not quite so fancy. But if you do have a fancy calculator, you may need to kind of, wiggle around with it, see how it works exactly. There may be more to doing this than what I'm showing you. I'm going to close the parenthesis. I'm going to cross my fingers and hit enter. And I'm going to get, woohoo, the correct answer. 613.6679 and some other things, which we are going to round because these are dollar amounts. We're going to round to 2 digits to the right of the decimal point. So that's 613. And I'm going to round to 67 because of that 7 right there means I go up. $613.67. Now, does this mean that every deposit has to be exactly this much? And the answer is yes and no. 39 of the 40 deposits will look like this. The 40th deposit will be used to take into account all of the rounding, right? Because I can't actually make a deposit of $613.6679, etc. You can't do that. So I'm going to have to do 67 cents and account for that in the last payment. Okay, very exciting. So $613 every 6 months at 2% will get you $30,000 in 20 years. Woohoo! That's pretty cool. So I did promise you something exciting. Are you guys ready for something exciting? Are you ready, Godzilla? Yes? Okay. So what I want to do is I want to show you, because it's a fair question, well, what if we, instead of doing it at the end of each 6-month period, what if we did it at the beginning? Is that going to benefit us at all? So how would your answer to the previous problem change if deposits are made at the beginning of each 6-month period? And so I'm going to pull out my lovely formula sheet. So I've got a visual aid, and we can say if your annuity, if the deposits or the repeated payment is happening at the beginning of each period, you have an annuity due. And this means that you have a little extra guy stuck on. Now, for the purposes of our of this video, it's getting kind of long. I'm already at 20 minutes. So I'm going to tell you that you can take this formula and using the same method we just used, but with a little extra guy stuck on, 1 plus I, you can actually get a different version of this formula. So let me write this all out so you'll see what I mean. This is, so the beginning, what color did I use for that? I used orange. Okay, that catches our attention, doesn't it? If it's at the beginning of each 6-month period, beginning means we've got an annuity due. So in other words, it's an annuity that's being paid at the beginning of each period instead of at the end, and that does make a difference. So we've got S equals R times the quantity 1 plus I to the nth minus 1 all over I. That's our usual formula, but because it's an annuity due, we get this little bit extra bonus money from having it in a little bit earlier, which is really nice. So now the question is, what does this end up looking like in our other formula? And so I'm going to do a little math. Yay, math. Yay, math. My client is very impressed. I'm going to look, I'm just going to do a little algebra for you. And the client's going to be like, ooh, you're doing algebra. And I'm going to say, yes, I am. You should pay me extra. So again, I know everyone, you may be looking at this going, what in the world just happened? And remember what I said was when you move this rational expression to the other side of the equation, everything flips upside down. And so if you're multiplying by 1 plus I, that means it's technically on top. So when you flip it upside down, it ends up in the denominator. So this is how we rewrite the formula for an annuity due. Okay, so let's take a look at what we had previously. I'll write it over here because this is where I have room. Remember that we were looking to discharge a debt of $30,000. Our interest rate was very conveniently 1% per period. Our M was 2 periods per year. Our N was M times T, which was 2 times 20, which was 40. Okay, I think I've got everything we need here. So I've got 30,000, 3 times 0.01 up on top. And then down the denominator, I've got 1.01 to the 40th minus 1. And then another 1.01. Now, this is going to make the calculation a little bit complicated. If you want to do this in one piece, you're going to have to use a lot of parentheses. So, are we going to be okay right there? Let's go through it. Okay. So, starting up top. Ooh, that looks like a decimal. That is a comma. I've got 30,000 times 0.01, and whenever I'm done with the numerator or the denominator, I'm going to make sure I hit equals. So the numerator is going to be 300. Now I'm going to divide by, and I'm going to start with one set of parentheses that include the whole denominator. So there's going to be like one big set of parentheses outside the whole thing. And then I've got a second set of parentheses that's just inside here to do 1.01 raised to the 40th power. I'm going to subtract 1, close that set of parentheses. So that's this one right there. And then I'm going to say multiplied by 1.01, close the big parentheses, cross our fingers, because, you know, this is a lot of pressure. We're 25 minutes in. And it worked! Yay! And we end up with 6, can't quite read it from my perspective, 607.59201 and some other stuff. And so that is, again, we can't make this payment unless we're a very big bank and we're just moving money around in that fancy way they have doing it. But regular human beings, we can't do that. We have to make payments in whole cents. So that's going to be $607.59. So what is the difference? Well, it isn't that big a deal. The difference between depositing it at the end and depositing it at the beginning is almost exactly $6. Now, why would the difference be almost exactly $6? Well, let's think about it. Approximately how much are we depositing each 6 months? We're putting in about $600. What's our interest rate per period? 1%. What is 1% of about $600? It's $6. So if we put it in at the beginning of the period, we save $6 because in that extra, right, if we do it at the beginning, that extra time, it makes an additional $6, which we have to compensate for. If we do it at the end of the period, we have to put in that extra $6 ourselves. If we put it in at the beginning of the period, then it's just going to earn the $6 all by itself, and we don't have to worry about it. See, that's the whole difference. Okay, you guys made it. Do you understand, Mr. Godzilla or Ms. Godzilla? Godzilla, how do you feel about this? And Godzilla seems to be a little bit concerned, but is okay as long as we smile and say, this is going to be great. And this way you can pay back all that damage you did to the city of Tokyo. Yeah, awkward. But with this plan, $607.59 at the beginning of every 6 months, you will have $30,000 in 20 years that you can use to pay off some of the damage you did to those buildings. So that's it. You guys are awesome. Hopefully this all made sense. If it doesn't, please ask lots of questions. And I hope you had a great day. I hope you had some vegetables, got a little sunshine if you can. And you guys are awesome. Woohoo. Math on. Woohoo.